Ooh, okay. So, right. So there's a small delay with streaming, so that's okay, but hopefully I'll be able to get my point across. So my Visual Studio looks a tiny bit different, because I've got a newer version that hasn't quite released yet, but it will be out. Ooh, let me check. I think it's March 7th. Yes. And everyone will probably be switching to this, but probably not AE because they're pretty slow like that. But doesn't matter. Anyway, but yeah, it's the same process. There's no project differences. You can still go file, new project, whatever. So I'm just going to create an empty project. There are a few differences with like console applications. I'm pretty sure Noman's been saying, hey, use console applications, but there's really not much of a perceivable difference for. Yeah, I can see that you're watching it. Sorry, you're probably weirded out by how I'm responding to your messages in my time, but you're sending them in your time, but it's like all out of sync. It's really funny. Anyway, but so we have Win32 console applications, Win32 applications, empty project, and makefile project. Don't worry about makefile. I usually stick with empty projects for the stuff that we're doing, but I think Gnomon specifically uses Win32 console applications, so I'll just walk you through what happens here. So you get this window, and you get a few things in here. So in the console application one, you get a few different ones than you would with the Win32 application one. But there's a few different types of application types. I don't want to get you confused, so don't think much of it. But Windows applications are like the one we're using now, like with actual windows and things like that. So if I actually create one of these, I'll show you. These are quite complicated for someone who's just started C++, but I'll show you what it looks like. It just looks like this. This is the application running right now. This is what it is right here. So there's a file, there's exit, there's about, simple stuff like that. And that's Visual Studio gives you that by default, which is really good. And it's quite complicated code, as you can see. There's lots of crap in here. But the main point is that it's all C++ at all. It's all sort of around itself. And you can see here that this API entry point right here, don't worry about what this actually is, but just see this. This is a function. If you get rid of all the crap, you can see that this is actually still a function in its core, basically. So here's our return type, and here's our function name, and here's the parameters. Just like in main, in a regular C++ program. So if I close the solution, I just create a new project. I'm going to choose Win32 project, Win project test, and we just want an empty project. They actually got rid of SDL now. It's one of those things that's sort of default, not really there, but because SDL is basically just like an extra testing level or an extra error level that Visual C++ uses, which is the type of compiler, because there's actually a few. There's a few different types of C++ compilers. So the main ones that we encounter as developers are usually the Visual C++ one, which is the one that Visual Studio is. That's Visual Studio. Okay, so a compiler is basically just what turns C++ code into zeros and ones, basically. Although it doesn't actually do zeros and ones, it turns it into a bunch of instructions that the processor can understand. But the idea is that it turns it from code that you can understand and that people can read, and turning it into binary or zeros and ones, or the executable code that the processor can understand. Okay, so the basic general premise of that is that it's really pretty simple. Yeah, I guess. Sorry, I'm just reading your messages now. Yeah, I guess SDL is definitely for dealing with issues like that. It's called the security. Oh, that's a good question. If you type it up on Google, you'll probably get an API called SDL, which is, well, actually, it's not an extra error level. I should be a bit more specific. It's more about the way that security works in Visual Studio, because or project security, and it's really not necessary for the stuff that we're doing. Say, for example, you were dealing with something that really needed to be pretty secure, not in necessarily in the sense of like hacking and stuff, but in the sense of making sure everything's working perfectly. Like when you're dealing with some really heavy memory stuff, I would definitely say SDL's really worth it for dealing with things like that, making sure it's quite perfect, basically. But in this sense, there is actually no difference between the Win32 application and an empty project, because they're essentially the same thing. So yeah, but I would stick with Win32 project or whatever Nomen says, because I'm a bit of a rebel, but that comes with me. Anyway, so I'm just create a call this console program, and it will give you a blank Solution Explorer. Your windows will look pretty much exactly like this. There might be a few differences, but essentially it's the same. So you get in your Solution Explorer, there's these folders and things. These are actually called, these three right here are called filters, and they're used like you might notice if you go to where your project was created. So for example, if I go open folder in File Explorer, I don't think this is a thing in the one you guys have, but in 2017 it is. So you see in this folder there is actually no source resource. There's no folder called that. These are called filters, and they're used to design or to filter code around. So what that means is I created a source file in here. I called it main.cpp, and I created another source file in this header file. I'm going to create a header file. I won't go into what these are, but maybe just call it header.h, and that'll create the file. And if I go back into that folder, you'll see that two things are here, but they're not in that source. Well, see, the thing with antiviruses is they have some really interesting ways of dealing with how programs execute. The way that they read programs and understand if they're an issue or not is quite it's like a bit of a cheat almost. And sometimes they can interpret programs like that use CN as viruses almost. It's really interesting. Anyway, but the idea of these filters here is really important, because you can use these to make your development environment much more effective, but you can still maintain the same kind of organization in the folder. So say for example you actually did want to create these folders in there, in the actual where the project is on your computer, so in Windows Explorer, so in here. So say you wanted to actually create those folders, what you could do is you need to press this little button up here that says show all files. Clicking that, it'll show you what's actually in the folder, and it doesn't show you all the project stuff, because Visual Studio generates a bunch of crap, right? And that's what this stuff is here. And it shows you the relevant information, which is your project files. It shows you the actual files in your project, so the ones you need to use. And if I wanted to create a folder in here now, new folder, but if I turn that off and I created a new folder, it's a new filter. Now, do you see the difference? It's pretty subtle, but there is a difference, and they're really helpful for creating work environments where, as a developer, you want to be a bit more effective in the way that you're storing your code in your computer. This might come in handy when you're trying to include your header file here that you created. So say you wanted to include, like, you know how we include IOStream, like that. This is in the main.cpp file. You can see that it's like, okay, cool, we've included IOStream. Now if we tried to open this, and you can actually navigate to open files by right-clicking, going to open document. This works, doesn't matter what version of Visual Studio, most of the time it's the same. This will bring you to the actual IOStream file, and you can see it's actually quite small, but there's a lot of other files included in here. That it's all very nested, like we've seen before. Are you a bit confused? How are you confused? Confused. So are you confused, or are you just saying confused? I don't want to confuse you, that's not a good thing. Wait for it to catch up. Oh, right, sorry. Yeah, I kind of brushed over that a little bit. I'm trying to rush through that. But, so basically filters are hypothetical. So filters are like pretend, and then folders are the same. Like folders are actual folders on your computer. So for example, if I navigate to where this folder is by right-click on the project in our Solution Explorer, open file in File Explorer, you'll see how it will show me the files, but in here, this doesn't actually show you the folders that are in here. It only shows you the code that you've included in your project, because your project doesn't necessarily represent everything in this folder. Like I create a text file in here, call it text.txt, and it wouldn't show up in here or anything because I haven't included it. But if I press show all files, what this does is it says Visual Studio, I want to see the files in the console program directory on my computer, which is this one right here. So if I do that, press that button, it will show me the text file that I just created in here. So you can see how if I delete it, refresh, it will go away. So you can see how these files are exactly what's in this folder, but when I press that button, it shows me what the filtered view looks like, because Visual Studio tries to be clever and it adds the things where you want it to be. So if you were developing a game, for example, and in Visual Studio you for some reason wanted to list your assets, you might want to create a folder in here. So in your show all files view, maybe in your program folder, you'd have like a folder called assets and config and engine or something like that. And in Visual Studio you want to be able to show that. If you show all files off, if you turn that off, you won't be able to actually see that code, or that not code, the stuff that's in there. So it's basically just a way for you to manage your code a bit better. Because as a developer, as a coder, you don't want to be seeing all those text files or all the picture files that are in the assets folder. You don't really need to be seeing that, and that's just an extra thing for Visual Studio to have to index. So what you can do as a programmer is use this show or not show all the files in the directory. So make sure the button's off, so it says it just shows you the filtered view, and what that basically does is it'll just show you the relevant code that you've included in your project. So I can actually right-click exclude from project, and that will go away. But if I go back into my folder, it's actually still here. It's just not included in my project. So say for example, you might have can't think of an example. You might have code that you don't necessarily need to see, so you can just exclude it from your project, and it won't show up, and it won't even compile. It'll just pretend like it's not there. Now, this brings up another thing. If I wanted to include file that I've already created, I can go add existing item. So right click add existing item, and I can click on it and it will include it in the project. Another way of doing that is if I press delete and then I press remove, remove, that gets rid of it from my filtered view. If I go in here, you can see it's got this little red squiggly line here that says it's not included. That's what that means. I can right click include in project. So you can see there's two ways of doing the same thing in this situation. I can let me just exclude from project, it's gone. I can go right click add existing item, click on my file that I want to add, or contrary, I can go into my show all files view, right click include in project, or I could also do the whole add new not new item, add existing item. You get the idea. So that's the whole idea of having filters and things. It's allowing you to manage your code better and be a bit more effective in the way that you're dealing with your code and other people's code as well, and other people's assets and things like that, because you don't need to be seeing that as a programmer. So this brings up an interesting point. So what if I wanted to include my header file, because this is what this IOStream file is, and this is what I was getting at before I went on a tangent. This IOStream header file here is actually a .h file. If I right click open containing folder, we can see that that's actually, well, it's not in this case, but it is actually representing a .h file. Okay, it's a header, that's what they call them. And the idea of it is that it's basically just a list of things. It's not C++. That file just represents using IO, which stands for input output. So that's how you can use cout and things like that. So if I did not include this, and I created a void main here, so keep in mind this is what we're using. This is going to be our function to entry. So this will be our entry point. That's what this is called. So main is our entry point, and you can see a good thing about Visual Studio is if you put a comment above a function declaration, which is what this is. So the difference between declaration and definition, this would be a definition, or it's also called a function prototype. Okay, so this is a function prototype, and this is a function declaration. So what Noman was talking about was the difference between these two things, and you can see how one has these little brackets here and one doesn't, and one has a semicolon. And we talked about how semicolons can be used to define the end of a statement. So basically, the idea of coding is that you make a bunch of commands to the computer, you execute them, and then it will do what you want it to do. So it's the same goes with coding. You want to create a bunch of statements, and then what that's going to do is it's going to turn that logic into a bunch of executional commands that the computer can understand. So for example, if I just handed this to my processor right now as text, it'd be like, what does that mean? I don't even know what that means. What the compiler does is it says, okay, hey, so we want this thing called void main. Okay, well that's a function, right? That's this hypothetical notion of a function. And then we have this void main, that's a definition of our function. So these two refer to the same thing. So if we actually hovered over this one, sort of. Okay, so here's the thing, we don't need that because right now we don't have anything above here that's referencing main. Yeah, so we don't need that. So basically, we don't need a function prototype to use a function. A function prototype is only necessary, say for example I had a function down here, I called it int sum, and I just returned a plus b, and then I have some arguments in here, a and b. Oop. Okay, so basically what this function says, it says, hey, I have a return type int, I want to be returning an integer, and then this is the name of my function. So it goes like this, it goes return type name, and then brackets, argument, and then either, if you're doing a function prototype, which is used to tell the compiler, hey, I've created this function somewhere else, I've declared it somewhere else, but here's where I'm defining it right now. So the idea of that is that you can actually create code that's down here and use it up here, because the way that the compiler works, yes, so the idea that this int right here means it can only return an int. If I created a float in here, x, and I called it to 10.045, right? F, and if you don't put the F right here, here's a fun fact, if you don't put the F right here, it's going to try and cast that to a double. So you can see that says double, brackets, double 10.4499999993, and you might be wondering, why is it 449999, not 45? That's a really interesting thing with the way that computers store floats, or decimal numbers. They store them in a way where it's a mathematical representation of the number. So I don't want to bore you with that because it is insanely complicated the way that that works. But the basic idea is that the sign bit, there's a few different ways of representing it, but the idea is that it represents it in such a way where there isn't 100% precision, if you get what I'm saying. But I won't go into that because it's way too complicated for even an entry level thing. It's just, or you're an intermediate, some people just, you don't need to understand how it works. But the idea is that this float variable here, if I try and return this, it'll compile and work absolutely fine. So if I take some, I call this up here, I'm invoking the function right now. Okay, so invoking means you're calling it or saying, hey, I want to run some, right? So I want to run this block of code right here. And that's what this means. And then I'm going to give it a couple of variables, even though they're not being used in this situation. And if I run this and I put a system pause here, now what this basically just says, I'll give you a demonstration of what this actually means. So I'm going to open up a command window in Windows. So what this pause does right here. So I don't know if you're familiar with the Windows command line, but don't understand the double. How so? Oh, good. Okay, so you understand that when you type pause, well, it'll actually say press any key to continue. So that's where it actually gets it from. It's not like a thing doesn't echo. Yeah, in Lua, I don't think there's a concept of doubles. I'm pretty sure there's a concept of floating point values or decimals. I think they're actually called decimals in Lua, like as in decimal. Lua float. Oh, I think it's represented as a real. I think it's called real, R-E-A-L. But the type real actually represents a double. That's what it is. So there's floats, which are called floating point precision value. So there's, okay, I better go through this. So in maths, we have this idea of floating point numbers, and it's a way of representing numbers using only their information. So we can use a bunch of, it's basically like a bunch of ints, but in a much more effective structure. And we haven't talked about how memory works yet, but when we get to that, you'll understand more of how that works. But yeah, so in Lua, there's this idea of a real, and what that means is it means it's a double precision floating point number. You don't think it's real? Maybe I'm wrong. I'm always wrong, so just get used to that. Let me bring up some Lua code. I haven't looked at Lua code for a very long time. Right. Sample code, that will do. There's a bunch of stuff in Lua that they've added. Oh, that's right. Lua does types really differently. But the basic idea still stands. Lua has a concept of double floating point precision numbers, which is basically just what a double is. And it's essentially just a more accurate float, or more accurate decimal. So if I put an F here, hover over it, see how there's actually less decimal points? Whereas if I remove the F and it tries to cast to a double, which means it just pretends like there's a double there, not a float, treats it as a double, you can see there's a bunch more decimal points. So we're going to leave it as an F because we don't need something that's that precise. We want to keep as many significant bits as possible, which is basically what these are. So if we remove the F, you can see how it becomes less precise. If I put the 5 there, it'll go 4-4, like I was saying before. If I put an F there, it will treat the significant bits in more significance because there's not as much information. Yeah. Well, it doesn't matter how Lua works. We're talking about C++ anyway. But so floats are basically just like decimal numbers that have a certain amount of precision, whereas doubles are more precise floats, basically. So they're very precise decimal numbers. But with that precision comes with the loss of significance, so it will treat this information in less significant sometimes. But that's floats. But the idea that what I'm trying to get across here is that basically C++ doesn't really come with anything. If I have a look in IntelliSense, which is what this little box is in here, everything starting with S will come up in here. Well, it'll jump down to the list of things. So in here, right here, yeah. So Yeah, decimals are weird in everything. That's just computers for you. So in IntelliSense will show you, this is a Visual Studio feature, and this will show you all the stuff that you can use right now. So even though I've typed S, it actually just jumped me down to the first S thing in the list. So you can see that as I'm scrolling through here, that there's actually, here's our sum function, and if I look at that and I hover over it, I can also, there's a new feature in here. I won't go through that because I don't want to confuse you because you won't be able to use it. But if I hover over it in here, it actually shows the STD namespace. So whenever we type STD : where we are scoping into, that's called the scope to operator, or it's actually called the namespace scope operator or something like that. And it's basically just telling you, hey, go into this namespace. And what namespaces are like, if I excuse the paint, so namespaces are like this. So here's a namespace. We'll call it mix, just as a random word. You can call namespaces whatever you like, although you probably shouldn't use numbers. So just use alphanumeric characters that aren't numbers. But so in this namespace, this is a namespace. Call it namespace. So this namespace mix here, right? Oh, I lost my namespace. Here we go. So this namespace, it can have lots of little things inside of it. It can have these functions. So pretend like this is, this here is sum, this might be minus, this might be plus, this might be multiply, this might be divide. So it's a way of, almost like a variable, but it's like, it's a container. Think of it more like a container. So I'm going to create a namespace right now. And this is good C++ practice, and I can't believe Norman hasn't even talked about this yet. I guess he thought it was too complicated, but I think you guys can handle it. It's not that complicated. So the idea of namespaces is creating false scope. Well, it's not false scope, but it's like scope. So I can create a namespace called, we'll call it, what's this? We'll just create a fake program. Let's call it game. Okay. So say we're creating a game, and we want to, this is basically where you'd put your application name. So say you're creating Fallout 4, you'd put FO4 here. Basically, you'd put the name of your project there, pretty much. So I'm just going to put game in here. We're making a game called game. In this namespace, I'm going to create a function called void game start. Declare it. I'm just going to say, oh, okay, well, I want it to see out. And you might see there's an error then. I'll come back to that in a few seconds. I'm going to see out, I'm going to game starting, ... I'm going to end the line with end L. And then I'm going to make sure I include, so because I'm using input-output functionality, I want to include cout, or include IOStream. So IOStream, like that. And you'll see, oh, well, why there's still errors there. It's because we're actually out of scope right now. We're in the namespace game scope. So if I hover over this, you can see it says game : game start. So we're in the game namespace. So in order to use cout, we have to scope into the std namespace. So one way of doing that would be going std : okay, and that would show you all the functions that IOStream has just included for you in the standard namespace, std, that's what that stands for, not sexually transmitted disease. It stands for standard. : meaning scope into, and then cout is what we want to access, which is a function inside of there. So it's basically just like void cout, like that. And then it's not as simple as that, but there's a bunch of commands that it's used to make it so that you can do that, so make it so you can actually put the little dashes or little angle brackets. That's how it gets information. But yeah, so basic idea, we scope into a namespace by going std. So basically that's just like going yeah, it stands for standard, and it actually comes with the standard template library, which is a C++ thing, which is really, really handy. And another thing I can't believe he hasn't gone through yet. It should be in the first thing that we go through, because it's just an amazingly diverse bunch of things to use. and it's used quite a lot in the professional sector as well because it's quite great for what it does. So endl I know is also in the std namespace, but you might think, oh, well, that's really painful to have to type std : every single time I want to type cout or endl. What we can do there is we can actually type using namespace std, so the name of the namespace, and Visual Studio is clever, so when you type namespace space std, it'll show you what and it gives you this little symbol here of brackets. So we go std semicolon because we're making a statement, just like some feminists do, but I won't get into that. Nah, I was just talking to one of my friends who's super weird about that stuff, so it's in my head. But yeah, making a statement to the compiler saying, hey, we want to be inside of the st namespace. So anything you can't find in the namespace that we're currently in, which if we weren't in the game namespace would be the global namespace or the anonymous namespace, and we can actually create things that aren't in namespaces by just typing namespace brackets like that, and it will assume that anything in here will be anonymous. It will be in the anonymous namespace. So if I created an int x right here, hovered over it, it'd be unnamed : x, which is basically just anonymous. So this would be good if you wanted to create false scope. You can also do that by doing this, but you can't do that unless you're in a function. So if you're outside of a function and you want to declare a global variable, like here we can still use x, but the minute we enter another scope, or basic idea is that you can create variables that are not going to get included in another file, but that's not really necessary in CPP files because you don't include those. But anyway, you can create anonymous namespaces too if you ever need to do that, but basically you want to be sticking with this. So we created a namespace called game, we encapsulate it with some brackets, and then anything in here now will be used as the game namespace. So for example, if I try to use game start down here, why do you think that doesn't work? I mean, are we waiting like 30 seconds for the answer? Why do you think we can't access game start? Let's see where I'm up to. It's sort of like include. So why do you think that we can't access game start right now? Because it's up here, I've defined, it's all declared. Why it says unidentified? What does that mean? Undefined, what does that mean? How do I fix that? You can answer the question? Game, yeah. It's in the game, what? Namespace, right. So how do we get into that namespace? Yeah, how do we get into it? How do we scope into it? It's all good if you don't understand it. I can go through it again. Yeah, that's one way we could do it. We could go with using namespace. So we could go using namespace game semicolon, and voila, that would fix the problem. Okay, because now the compiler's looking in here as well as the one we're already in. So we're in the anonymous or the global namespace right now. So the compiler was, if we remove this line right here, is only looking in the global namespace for these functions. Since some is defined in here, it will be able to find it. and system pause is defined in the global namespace in IOStream. But our game start function is defined in the game namespace, so we have to type either using namespace game, capital G, the case does matter all the time, or instead of doing that, if we were only doing it once or something like that, we could type game : which is the scope 2 operator, and notice how we're getting all these other functions that aren't actually defined in here. The reason why that's happening is because in here we've actually scoped to the using namespace std as well. Okay? So you don't have to define it in another namespace. I'm going to get to what I mean by namespaces and where they're used in a second. So main has to be outside of a namespace, or it doesn't have to be. Sometimes I think it's okay when you don't. But generally, I would say always just put main outside of a namespace, because it makes more sense programmatically. So let's create a little fake game here. And that's a good example to start with. So I'm going to create a bunch of functions now. So I'm going to create a void game start. I'll declare that. I'll make it cout. Cout game starting. And then, so we don't actually have to put it outside of a function. You can also say using namespace std inside of a function, and that will also work, which removes the whole problem of inside game there being a bunch of other things. Like for example, if I put this up here outside of the scope of the function, you can see that when I type game : and I scope into the game namespace, we get all this crap from inside of the std namespace as well, because inside of here we've scoped into the std namespace. So by doing it inside of a function scope, what we can do is minimize all that crap, and it's called declutter, or making sure the global namespace is really clean, which is what we want. Same with any other namespace. We don't want there to be a bunch of stuff that we don't need in there. So now we can access our game start, which we've got, and maybe we want a function called void game loop, because in games we have this idea of a game loop, which is recursive. Well, actually, that's a bad word to use. It just keeps going. It's not recursive, it just keeps looping over itself. And the way we do that is by using a while loop or a for loop or whatever you want, but in this situation it would be much smarter to use a while loop, because you created a for loop and you said int I equals 0, I is less than, I don't know, 1 blah, 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 iterations, I plus plus, or plus plus I is what you're supposed to do. Everyone does plus plus I, or I plus plus. In this case it doesn't actually matter because it's executing in different places. But if you wanted to increment a variable specifically, and I'm speaking way too fast. Let me chill down. Getting excited. I get excited when I'm teaching people stuff. So plus I basically just means increment I and then deal with it. So there's really no example with a for loop where you'd use it the other way around, because it doesn't change a thing. Putting it here and putting it here doesn't change a thing in a for loop, because it goes here and says, okay, define a variable int in this scope, in the scope of this for loop in these brackets, and make it equal to 0. Then whenever it's, so I, if it's less than whatever that number is, then increment it by 1, which is what plus plus means. So whenever every iteration in here, if we type cout I, what would happen is it would print 1, or it actually print 0 to that number right there, or it actually probably print 0 to 10009 or something like that, because it wouldn't print that number, because it's saying when it gets to this number, stop executing. So the way we fix that is by going less than or equal to, and then it would actually print that number right there. And that's just basic stuff that we've gone through, and have a look at Noman's lectures if you need a bit more clarification about that. We wanted to scope to this, we'll just scope to this here because we're only using it once. That's my general rule of thumb, is if it's a one-time only thing, we can scope to it, but otherwise using namespace std is usually what we want to be doing. Anyway, so that's for loops. You wouldn't use that in this situation because you want this to continually, you want it to pretty much be infinite until you tell it to shut down, right? So we'd basically have a condition like while, I don't know, game.shouldClose is not equal to true. So basically we'd have this hypothetical variable called shouldClose, or we'll create it. Should close, and this is going to be a bool. We'll create a bool variable here. We'll set equal to false by default because we don't want it to close immediately upon execution. There really is no bad things that can happen. Well, that's a bit of a lie. Don't be scared about running loops for too long because it doesn't matter. Like, we could run that one before, it would probably run into some issues with memory, but apart from that, it wouldn't do anything. It's not going to crash your computer. There are very few things in C++ you can do as a bit of a beginner to F up your program. Very, very few things. But when you're dealing with things like this, it doesn't really matter. So we're saying while should close not equal to true. Basically, what's going to happen now is if I run this, I'll say running and L. And L. And then I need to make sure I'm scoping into a namespace, using namespace E. Move it to the top, because top's where it should belong. If you're using it inside of a function's scope, to prevent you from having to clog up your own namespace, then yeah, you're going to put it at the top of the function before you start doing anything else. And basically, if I ran this right now, what do you think is going to happen if I ran this? Or excuse me, let me write game loop. What do you think would happen right now? Not sure? Hey, that's what the big green button that says Windows Debugger would do. Hey, look at that. So, what's happened here? Well, we can see that this is just going to keep going on forever and ever 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 until this should close variable is not equal. Well, actually, that's a bad example anyway. Actually, no, that's true. No. We want that's a bad condition. We want this to be equal to true, basically. So this should close variable is equal to false by default. It actually doesn't matter because not equal to false is the same as equals to true. In this case. But we can see that in here, this continues to run. And notice how, if I comment this out right here, and I run it, you'll see it pop up and instantly close. That's because the way that the functions are invoked is it just continues and continues and continues forever and ever and ever until this function has come back. Like, until it's returned. Even though void doesn't return anything, it actually secretly does. Like, down here, it uses this. This is a perfectly valid thing to do. Basically, if I put this right here, and I ran this, what do you think would happen? I'll give you a minute to think about it. What do you think would happen if I just left that there, right there? Thinking about void and how it should return nothing. What do you think if I put a return there, right there? You got it. The loop will stop. If we run this right now, you'll see it opens and then instantly closes. And if I actually just set a breakpoint right here, using Visual Studio, you can set breakpoints. Right, if I click on the line that I want to use, so which is line 21, click there, in this little white bar over here, and I ran this, it'll stop at that return, or it should do at least. Actually, here's a good point. Because, man, I can't get this condition right, can I? So this is a good little funny thing. So basically we're saying, while this is equal to true, then run this. But because it's equal to false, it's not running it at all. So we actually need it to be not equal to true. Like that. So I've got it right now. That's perfect. Now if we run this, we'll hit the breakpoint. See how little things like that can make your program totally broken. So now if we see this, you'll see I actually ran once. You can see it says game running once, and then if I pressed continue up here in Visual Studio, it will close because, oh, not recompile, hold on. Close. Close. Let me close that. Oh, I knew this would happen. This always happens. There we go. Okay, so if I run this now, it'll instantly hit the breakpoint. If I press continue, it will close. Okay, so that's what that return does. Okay, so that's basically just a way for you to stop anything from happening. Another way you can do it is by typing break, but anything down here will still execute if you use the break, because it just breaks out of the loop. It doesn't actually break out of the function. So think of a return like a break, except it breaks out the entire function. Okay, so you can't use it like this when it's an int. For example, if I ran this, this would be invalid because it's returning. Actually, I think that just returns 0. This is an interesting example. Let's type int x equals that. We'll type system.pause or system.pause, system pause like that. Local Windows debugger. Let's run this. Oh, we got errors. What's the issue? Here we go. See, it says game loop must return a value. See, this isn't valid right here because it's not returning a value. So, for example, right here, you'd probably type return 0. And what that would do is that would exit your function, set x to 0 right here. This would return 0, which makes x 0, and then it would just system pause. Okay? So, that's a good way to do it. Or another way we could actually do it is we could say like, whoa. Hey, Visual Studio, chill out. So let's create a fake little game here, I guess. So let's create. I'm just trying to think of this. I don't want to introduce you to too much. I want to. Yeah, returns are really helpful. They're really great for dealing with different function types. So I want to make this a void because a game loop. Well, actually, in the industry they use ints because it allows you to return something. So right here, maybe we could have like a check of saying, okay, well, if the error event manager dot returns error or something like that, you know, if it returns an error that's fatal or something, then we want to exit out of this loop, or we want to just totally stop doing what we're doing and close the game like immediately. Well, actually, it'd probably be like if event manager dot get error is not equal to no error or something like that. Let me make this a multi-line comment. So you know how comments work. I'm pretty sure it's the same in Lua. It's, you know, comments like that. So let's just say we had this hypothetical object called event manager and it had a function attached to it called get error. I won't. Well, I'll go through it a little bit in a second. Let's do this. Let's do this. Come on. If you're keen to hang around, we can go through this. This might take a little minute. So are you keen to hang around? Okay, cool. So let's say we wanted to use let's create a little pretend game here. So I'm gonna create a manager dot get error. Well, actually, that's not going to work, is it? So let's go through some really cool things about C++. So you're probably wondering, why is it called C++? And I don't know if you've ever heard of C, but there used to be a language called C. Well, there's still a language called C, but not many people use it anymore because there's languages like C++. So I'll show you some C code. C code versus C++ code. See if this comes out with anything. Why am I getting so many emails today? That's a bad example. Anyway, but the difference between C came with nothing. It was basically just a bunch of extra things, like IOStream that didn't exist in C. IOStream's a new thing. STL, which is that standard template library, which is in the STD namespace. That's a C++ thing that came with C++. And the reason why that's a C++ thing and not a C thing, so there's two different languages here. There's C and there's C++. C was a really old language that was majoritively used with things like Windows 95. Well, actually, that's a bad example because C++ is around then. When was C invented? Is invented by a guy called Dennis Ritchie, and C was invented. Well, the first compact disc. Oh, no, that's bad. When C was invented. Programming. So, C pretty much came out in 1972. So that's over 40 years ago. So it's a pretty old language. And just to give you some context, C++ isn't really much newer. It's not like 2015 or something. C++ was invented by this really cool guy called Bjarne Stroustrup. And, I don't know, look up a photo of him. He looks like a pretty cool guy if you ask me. But C++ was invented in 1983. So it's still like over 3 decades old. Yeah, it's insane. So we're dealing with some almost old stuff, but they also keep it updated all the time. Like the last time this was updated, I think was 2014 or something. It was a few days after my birthday. My birthday's on the 1st. Yeah, it's on the 15th of December. 2014 was the last time C++ was officially updated. And it's not updated, it's a weird kind of updated because it's run by these people called ISO, or it's built on this standard called ISO. And what that means is that it's basically just a bunch of things that any C++ compiler should use. So like I said before, there's multiple compilers. Visual C++ probably has the same things as GNU C++ compiler has, which is like a generic one that a bunch of people created that's open source. In a weird sense, it's not open source as in you can't like change the compiler code or anything, but yeah. So there's a bunch of different things that C++ should have to use. And that's what the ISO standard does. But, well, yeah. So basically, yeah. So C++ is a bunch of, it's like built on a spec, basically. So if you've ever dealt with, like, you know, in engineering, how we have a bunch of like plans, things like that. Basically, a bunch of people went out and they made like a plan for C++, what it should include and how it should include it and what ways it should do that and things like that. That's what the ISO spec does. And C++ 11, or it's probably C++ 14, uses that, basically, okay? And it's based on C. C++ is literally basically C plus things. And one big thing that came with C++ was, number one, the STL library, or STL, which is Standard Template Library. And the reason why it's called Standard Template Library is because it uses these handy little dandy things called templates, which allow you to create dynamic code. Now, dynamic code, you might be asking, well, code's pretty dynamic anyway. So let me ask you this. Let me approach you with an interesting problem. So say I had a function. I wanted to create a function that was sums two numbers together and returns a plus b. Code can be dynamic, but it also can be not, and in this case it's not. So I'll show you what I mean. So let me approach you with this problem. If I said, okay, I need you to create a function that takes ints, doubles, floats, adds them together, how would you go about doing that? You'd probably answer with overloading. You'd overload the sum function with function overload. So you do it like this. You go, hey, I want a function that goes float sum, float a float b, return a plus b, and you can see how repetitive this is already becoming, and if we've only got two. Double. Oh, no, that's right. So you can see, oh, we have these three functions that literally do the same thing, but the only thing that's changed is these three things right here. How can we make that dynamic? And that's what templates try to answer. Or templates answer. So all we need to do to use templates is just type template, some cool little square brackets like that. You can put a space there if you want, but most people don't. And then type name, capital T for type. You can actually specify multiple ones, but you don't need to do that here. So basically what we're saying now is every time we put int in here, we're just going to put T like this. Okay, and it's just going to say, oh hey, so you're creating a function that uses this pretend type. I'll go through. So overloading is what we were doing before by creating the same function with the same name but different variable types and different parameters. So that's what that was. So let me go back to that. Sorry, I'm getting ahead of myself again. I do that all the time. Just pull me up like I just did then whenever you have an issue or have a question. So basically, if I call sum in here like this, you can see that it says one of three, which means there's actually three versions of this function I can call. So if I press arrow here, I can go through them and you can see how, hey, there's a double, there's one for float, there's one for an int. See, there's three versions of the same function. It's the same name. There could maybe in this case be double C if you wanted, or maybe there might only be A, and it just returns A. You can see how it doesn't really matter what you put in here, it's still going to have three overloads, right? See, there's three overloads, and that's what these are called. This is an overload, this is an overload, and this is the original function, but it's also classed as an overload. So by overloading, I don't know why they called it overloading, but it basically just means creating a function with the same name as some other function with different parameters and a different return type, if that makes sense. So you can see how this function here called sum has the same name as this one, has a different type to this one, and it has a different parameters as this one. They can have the same number of parameters or whatever, they can have different parameters, doesn't matter. They're overloaded, which means there's two different types. Okay, so you can see how that can be really repetitive by having to go through and change all these types from int to float, or from float to double to whatever. You can see how that's quite repetitive. The overloading way was the C way, and now the new C++ way doing things is by using templates. And templates are only really good in a few situations, but we'll go through this one. So template, type name T, capital T, don't use lowercase t, you look like an idiot. And then basically we're creating this dynamic function right here, T. It's called template meta programming because it's meta, like it's all sort of about around itself. It's kind of weird. Look up, there's some really interesting papers. So when sum is called, so if we called sum when there was three overloads, okay, there we go, cool. So there's three overloads right now. I'm just going to go back to the two parameters here. You understand that there can be multiple parameters. It doesn't have to be two, it doesn't have to be the same number, it doesn't have to be the same letters. Basically, this is an entirely different function with the same name as that one, basically. So right now, if I called this function, it's going to ask me what parameters I want to give it. So I can give it a double, I can give it a float, I can give it an int. And you can see when I mouse through those, it's gonna guess, or it's gonna tell me. So say, okay, well I want to add two floats together. I'm going to type, I want it to get the result. So the way you get results and stuff like that is you create a variable called float x, and then you can say equals to sum. And immediately by just doing that, it's going to guess that we have. Well, Visual Studio is not that clever. I should stop assuming that it's clever. 0f, 0.0f. So you can see right now, look, it's just like, it's fine, there's no issues at all, because it knows that there's an overload for sum that returns a float, which is what this basically says, okay? So it says, okay, we want a variable called x, and we want to set x equal to whatever 10.0f plus 0.0f is, which is obviously going to be 10.0f. And that's what this sum function does, and it goes, okay, hey, there's a function called sum, and it takes a float and a float. Oh yeah, there is. That's right. There is a float. There is a function called sum, and it takes a float and a float, and it returns a float. Cool. We're all good. We want to use that definition. So any code in here right now that will get executed. Say we change this to double, and we have to remove the f's here for it to actually use the doubles, because it will assume that you're talking about doubles when there's no f there. When you put an f there, it's dealing with float. Okay. And notice how the float one works perfectly fine when we put f there. That telling, oh hey, we want to use the float, it'll just return a float and cast it to a double. Really easy. I don't know if there's a concept of casting in Lua, but the idea is that you can just turn a data type from another one into another one. So I can convert a double into an int. What that will do is it'll just cut off all the significant digits from the other side, so anything beyond the decimal point, it'll just get cut off. So this, if we tried to cast the result of this, so when we run this right now, let me just put a breakpoint right here on this right now. Oh, it always does that with returns. It doesn't, it's not clever enough. I have to just, to create a breakpoint, you have to have something on the line. Yeah, so numbers are all the same, and you can move data around with different types. So we can create an int x equals x, or call it w or something, I don't know. So if we ran this right now, and we pressed local Windows debug, I've set a breakpoint right here. So we just stop right here. So we can see that x returns 10 because, yeah, that's right, it is a plus b. And it's using this float one because we specified that we want to give floats. So if I get rid of the f's here, so if I close this, if I get rid of the f's here, actually that's a bad example because that doesn't make sense. Let me do that. So you'd assume that 10 plus 11 equals what? 21. So when we run that, we expect x to be equal to 21. Well, no, because we're using the the float version, because we told it, hey, we want to use floats with these f's here. And that only works when you're dealing between doubles and floats, because they're essentially the same thing. They're just more precise versions of each other. If it was like an int here, it would probably guess that it wants to use the int. Or in this case, because we specified in the function that we want to give floats, it'll just cast whatever the result of this is to an int. So because we're dealing with floats here, it would just return. Let's change this definition. So you can see how the float version of this function, return a, it only returns a, it doesn't return a plus b like the other ones do, because it's different. We can make it a plus b, and we will make it a plus b just for the sake of this example. So when I run this right now, you'll see that x will probably equal to 21 because we're dealing with the float version of our function, because we specified that with the f's, okay? And it will return the number, except it's going to cast to an int, which means it's going to remove all the significant digits. So if I make those random numbers like that, you'll expect, oh, well, why wouldn't it be 10 or 21.51? It's actually only going to be 21 because it's just going to cut off those numbers. It won't round or anything, it will just cut it off. It doesn't round because that's not how it works, okay? So this is a really common pitfall for programmers to run into, is when they're dealing with different versions of the function. And that's what templates try to solve, okay? So do you have any you got lost? Okay, where'd you get lost? Overloading is a complicated concept. Floats. Okay, so floats, we know what floats are. They're basically they're single precision decimal numbers, which means that it can only go up to a certain amount of decimal points, because computers deal with floats really weirdly, and it's not like real numbers in real life where you can write down, you as a person can interpret a number that's infinitely long. It doesn't matter how long it is, right? But computers, they have a finite amount of memory, so they can't just store numbers that are infinitely long. So someone made a decision, hey, we're going to have these floats, and they're going to be equal to whatever number. So if I hover over this float right here, and it's designated by a float because it's an F beside it, this could be a capital F, this could be a lowercase f, has to be an F. And what that tells the compiler, hey, this is a float, this is a literal float, I think you might understand the definition of literals and variables. Variables are things that can change, and literals are literal things. Like, for example, this right here is a literal, whereas if I typed float f equals 10.0f, and then I gave it f, that would be a variable. Okay, well let me call this variable. That's probably a better name. Yep. So when I give it variable, we understand that that's a variable that changes, varies, variable. Whereas if I just put this number right here, we're using a literal. That's literal. That's called a literal variable. Literal variable. Oh, variable. Literal variable. Literal variable. Literal variable. Literal. Make sense? Cool. So, now if I hover over this, you can see. Well, this is really interesting. I don't know why it's doing that, but you can see if I hover over this one, you can see that it's if I hover over it, it says brackets float 11.199999981. So you can see that there's that precision. It's not just showing you a random bunch of numbers where there's no zeros. That's the maximum precision that it can handle. Okay, so that's the most precise version of 11.2 that floats can handle. Okay, if that makes sense. So in the float data structure, which is a total of, I think it's like 26 bits, which is essentially, I think the largest float you can have is 3.402823 times 10 to the 38th. That's a pretty large number, right? So it's essentially 2 to the 127th. Okay, so it's a pretty damn large number, approximately. So that's the maximum number we can store in the float. But when you're dealing with doubles, it's an even larger number. It's 1.8 times 10 to the 308th. So that's 308 zeros beside 1.80 up to 300. So that's a lot of zeros, and that's a big number. So you can see how there are actually limitations, but most of the time you won't hit them unless you're dealing with some like crazy space calculations or something. So that's the difference with floats. Floats are smaller and doubles are bigger and more precise. Floats are not so precise and doubles are really precise. Okay, so most of the time just use floats because doubles aren't really necessary. And they're also typically 64 bits, whereas floats are usually 32 bits. Yeah, so you don't need to understand what that means, but that basically just means that, hey, one's bigger than the other. Okay, so with these overloads right here, so we have overload 1, 2, 3, doesn't matter what order you number them in, but yeah, most of the time the amount of precision is really not necessary, just because of the way that the stuff that you're dealing with. Even really complicated rotations, like when you get to coding for math for games, which is a subject that AIE offers in the advanced diploma, you'll probably do it in, I think it's study period 3, if I'm precise. I'm not sure. I don't know the study plan off my head. Study period. Let me just check which one I've got it under. Yes, so math for games is study period 2. So next study period, which is going to start pretty shortly, you guys will encounter math for games, and you'll start dealing with some rotations. And those rotations can be sometimes need some more precision than others. However, most of the time, you don't need more than 9 decimal places of precision, which your float will probably get you away with. Okay? So just think of that. So when you're dealing with really important precision numbers, doubles are your go-to. That doesn't necessarily mean yeah, decimals. Most of the time I'll just round to 2 decimal places, but sometimes, you know, when you're dealing with a game, you want to be pretty precise sometimes, because that tiny little bit of precision can sometimes show up on the screen, and make for a pretty bad experience for the player. So it's important when you're dealing with things like that. Yeah, so it's basically just like You just got to really think about the use cases, and it'll come down to whatever your math for games teacher says, something like that, stuff like that. But just get into the habit of really thinking through what you're coding and understanding, hey, do I really need to use doubles here? That kind of optimization is something that you can only really learn from time. So just get in the habit of really thinking before you're coding. Have an idea, plan it out, use a piece of paper, say, okay, well, like tic-tac-toe, I'm going to create a function that gets the player's input. I'm going to create a function that puts that input into an array, and I'm going to create a function that takes that array and then checks if it's a winning array. If it is, then return true. If it's that sort of stuff, you got to plan it out on a piece of paper on your computer or something like that before you really jump in and start coding, because you can get totally lost. And I can attest to that, and it's taken me years to get to where I'm right now, and how good planning and things like that can really, stuff like that. Yeah, optimization in C++ is usually pretty simple, because when you're dealing with little things like doubles and floats, it doesn't really particularly matter. If you're on a console, on a gaming console, and I'm sure you'll get to understand this maybe later down the line in this program, that there really is a really small amount of memory to deal with on a console. 8 gigabytes is typically about what it is right now. I think they're actually in the next console, but you didn't hear me say this. The next console is going to be 16 gigs. I think the Xbox Scorpio might have 16 gigs. But again, you didn't hear me say that. But yeah, so you can see there's a finite number of memory, whereas on PCs and things like that, memory is a lot more expandable. But yeah, so just think about that when you're dealing with floats, like stuff like this. But anyway, so let's go to templates. So games can be quite large in their actual content, right? So think about GTA 5. GTA 5 is 60 gigs. Well, it's actually more like 67 or 68 nowadays, because of all the updates that they've pushed to it, or the DLC. That game is 60 gigs. Number one, because of textures. Textures are friggin' huge. They're insanely large. Because they're actually binary. You can't store textures as text. It's actually, you just can't do that. You have to store it as binary information. And you won't understand what I mean by that until you've dealt with binary files. And we'll come down to that, I think, a few weeks time with RAM. But yeah, you'll get the idea when we come to that. But the idea of that is, obviously, let me see if I can bring up a texture. Let me run and grab a texture. And games like GTA 5 are clever. Or .dll files. DLL files are really, really cool, because they don't make any sense. DLL files can be quite large sometimes. Let me jump somewhere and I'll find a texture for you, and I'll show you what textures look like as text. Let me open up a game. Oh, I don't think they store games like that. Actually, you know what? That's a good example. Steam apps, common, Fallout 4, data, here. So let's just pretend for a second that this is a texture, but this isn't actually a texture, because it's actually a BA2 archive from Fallout 4. But just pretend this is like a texture. See how much text this is? This is a lot of text, and that's how it's got to store it. It's got to store it as text and a bunch of random symbols that then gets interpreted as pixels and information like that. And this probably leads me on to how that actually works. So basically, what happens? Let me bring up Paint again. Delete. So basically, it just has a bunch of this sort of structure. So there's this structure, and then it needs to turn that into a bunch of zeros and ones, and then it gets pushed to a file, and that's what we just looked at was, pretty much. Okay, so that's the result of this big structure being pushed into a file. Okay, we get stuff like this, and that's really good because it's really secure. It allows you to secure your code and your information better when you put things in archives, and that's why games use archives. Like here's Fallout 4's data folder here. You can see that there's these BA2 files, and they're like two to 4 gigs large. They're pretty big files, and you can see that there's multiple texture files that are like larger than 2 gigabytes. So you can see that's a lot of stuff, right? And they'd all be full of things like this, which are texture structures that have been turned into zeros and ones and written to a file as text, and that's what this is. And then the opposite thing happens. It goes, hey, file zeros and ones, and then we're just gonna like take that data and then like push it into like a mold, and it will come out as that structure in code. So for example, let's create our own structure here. Let's go through this right now, just because this is cool, and I'll show you what I'm talking about. Okay, so we're going to create a structure, and in code there's this thing called struct, and struct is short for structure, obviously. And I'm just going to call this, let's just call it texture 2D or something like that. I don't know. And then we have an int x. We'll call that width, int height, and then we'll have an int. No, they wouldn't necessarily be smaller in size because they're actually just like this, and I'll show you what I mean in a second. So I'm going to create an array of pixels. Actually, I'll make these const. So const basically just means this number cannot change at all, and since it hasn't been set yet, it will, yeah, but don't worry about too much like that. Basically, when you put a const here, it means this number cannot be changed as at all. So if I created a const in here, const int x equals 10, and I said, hey, I want x to now equal 11, it's going to say, hey, x is actually a constant and it can't change. Okay, so that's what const does, and we're making this number a const because we can then use it as an array subscript, and I'll show you what I mean by that in a second. So we'll call this pixels. That, and this is going to be width, height. I think this should work. Non-static minimum reference. I think this has to be a constant static. Constant static. Oh no, okay, that doesn't work. Anyway, but the idea is, yes, there would be an error, and I showed you that before when we said const int x equals 10. When we tried to set x equal to 11, it would be like, hey, there's an error right here. Expression must be a modifiable L value. Whatever that means, right? That just basically says, hey, you can't change this value because it's set to read only. Okay, so I'm going to create this. I'm going to create this texture hypothetically that's, let's just make this a pointer. Yeah. So pointers are really cool. So pointers allow you to create references to memory locations, and I know that sounds really scary, but it's not. So let me look at memory diagram, and it took me ages to understand pointers, and I'm going to try and sort of explain to you how this works in a simple step. So here's a cool little diagram right here. So do you understand the concept of an array? Okay, cool. So arrays are stored in memory like this. They're stored one by one like that. Okay? Yeah, it's practically a table. Really, it is. So if we think of memory like that, we look at this diagram right here. Hopefully this should explain it a little bit better. Okay, so this is what memory looks like on a computer. And an int takes up 4 bytes of memory. So each one of these each one of these rows here is a byte. So think of it like that. So you can see that at memory address 9 billion, or sorry, 90 million. Is that 1, 2, 3, 2, 3, 90 million? At memory address 90 million, it's the start of this int that we're trying to represent. Okay, so whenever we create an int in memory, so when we type int x equals 10, we're saying, hey, can you reserve a bunch of memory here so that we can create this variable called x, and we want it to be equal to 10. Okay, that's what that is. That's what it's saying. And you can see how it just stores this as zeros and ones. It actually, you can see it here as hexadecimal, which is another way of representing numbers, but you don't need to understand how that works. Just understand that those 4 rows right there represents the int. Don't need to understand how that happens. Just think of it like that, okay? So it is kind of mind-blowing how this works. It is really crazy. So a pointer, okay, so the idea of a pointer, okay, which is what this little star right here means. A pointer is a pointer to that address. So it's like an arrow, basically. So let's have a look. So let's create an int pointer here, x, and right now this will just be nothing. So if I tried to print this out here, so if I typed, just pretend like that struct thing right isn't there, int space std, int x is 0, int var car equals 0, just for a breakpoint right here. So I want to break. Okay, cool. So you can see right now it just says this pointer, if I hover over it, which would usually show me what it is equal to, this pointer is equal to 0xccccccccc, which is basically just hexadecimal for nothing. Okay? Or in brackets it says nothing, or it says unable to read memory, because the memory that it's trying to access right now is nothing, and it's getting confused. So if we set this equal to null pointer, null ptr, that means no pointer. Now we run this again, we'll probably get the same result, but we might get 0, 0, 0 this time. Yeah, there we go. So 0, 0, 0, 0, 0 means nothing, right? That makes sense. So this is pointing to absolutely nothing. Say we wanted to make this point to our car variable right here. So let's create a car, we'll set it equal to 10. And we wanted to create a pointer to car. So if we could type car here, it's like, oh, why is it's got error? What does that mean? Oh, we can't, it's not the same. So think of int pointer as its own type. Like, you know how an int is a type? Int pointer, that's its own type as well. Okay, think of it like together. Don't think of it like, oh, it's an int pointer. Think of it like int pointer. One word, one thing, one object. Okay, because that's what it is. It's its own type. Okay, so we can't set, just like we can't set a float 10 or float variable equal to car. Well, we could, but you can see what's going to happen is it's going to implicitly cast from an int to a var, or into a float, which will just basically mean 10.0000f, which doesn't really matter, but pretend like this was an error right here. It says, oh, you can't cast from an int to a float. Basically, that's the same thing that's happening here. You can't cast from an int to an int pointer because they're different things. Okay? So if we wanted to get a pointer to this variable right here, this one right here, so remember pointers are pointing to something, okay? So if we wanted to get a variable, a pointer to this car variable, we type the ampersand before our variable name, and that means reference of. Okay, that's called the reference of operator. What that means is it means, hey, I want to get the memory address of this variable. So if I ran this right now, oh man, I wish you could just create breakpoints like that and run it, and they'd actually execute. That'd be really nice, but they don't. System pause. There we go. Let's run this now, and it's just going to stop where it is right there. Cool. So if we look at X now, it's given us this crazy memory address. It's X 0x00E1F794. Okay, so right there, basically, that is, pretend like that number right there is equal to 0x whatever whatever. Okay, so that's where the int starts. Okay, so that's where the int starts. So it starts reading memory from there. It'll read 4 bytes, and that'll be where it stops. Okay, it's pretty clever. It's very ingenious. So now we have this pointer to x. You're probably thinking, what the hell do we need a pointer to x for? We've got it right there. We can just type. Oh, sorry. We've got a pointer to car. Why do we need to create an int pointer to car? That doesn't make sense, right? We don't need that. We can just type car equals 10. not have to go, hey, x, and if you have a pointer of something and you want to get the variable that it points to, you can put the little pointer in front of it and then type equals 11. And what that means, that's called the dereference operator, and that dereferences it, so it turns it from this into a regular variable. So this basically just converts an int pointer back down to an int. So now we're basically just saying, hey, and if I press yes and run this again, you'll see that x is now, or car is now actually equal to 11, because our pointer, we were using our pointer to change it. Okay, if that makes sense. I know this is super abstract and makes absolutely no sense at all, but just bear with me here. So now let's create a variable in okay, here we go. Here's a good example. Let me think for a second here. Okay, so let's create our struct. Now we sort of understand how pointers work. Let's create our struct. Let's create a texture 2D object. Okay, so this struct, we're creating an object. A struct is a, it's like instructions on what it's like a recipe basically. So a struct, and I don't know if you've ever heard of classes. Classes are pretty similar, but a struct is basically just like an instruction manual on how to create something. So this struct right here, a texture 2D, it's an instruction manual for how to create texture 2D objects. Okay, everything is object in C++. You got to think about it like an object. So a struct is an object, a class is an object. They're all like recipes basically. So we want to create an object right now. So we're going to call it texture 2D. We'll call it texture 1, and we're going to set equal to new texture 2D. 2D. Right. So we're going to run into some issues right here. Firstly, we can't use the new right there. Pretend that's not there. I'll tell you. Excuse me. Okay, so we create this texture 1 right here. What's the problem? It can be referenced. It is a deleted function. Oh, we might have to create texture 2D like that. There we go. Okay. Sometimes you'll have to create this constructor. What this basically is called is it's called a constructor, and all it does is let's just get rid of those. I think that's what the problem is. Since it's a const, it runs into those issues, and it needs those const variables to be set. Otherwise, it doesn't know what they're set to. Oh, that's okay. You didn't miss much. You only missed my entire explanation of this entire concept that I've been trying to explain for the last 10 minutes. But that's okay. So let's just say we have this object texture 1, and it's of type texture 2D. So we're creating our own type right here. Okay. So you know how we have ints. You know, we're creating our own type, and it's called texture 2D. We're creating a texture 2D variable that's called texture 1. And by default, we're just setting all the numbers and everything inside of our structure equal to nothing. So if I run this right now and I show you what texture 1's equal to, you'll see that it's equal to a bunch of crap. It's like, oh, we didn't even set that. Why is that? Why? Don't understand. Why is it all crap? It's because it's practically just creating this variable and setting it equal to whatever it can find, right? So to get rid of that, we have to make it equal to texture 2D. Texture 2D like that, and we need some brackets like that. So what that basically says is, hey, I just want to set this equal to a blank 0 structure, so nothing inside of it, and you'll see that everything's set to 0 now. So whereas before, if I go back here and run this, you'll see it'll just take some random crap. Oh, stop. I'll stop. What's up? What's wrong? Oh, really? That sucks. Well, this will be available on this YouTube channel when it's done, so you can rewatch it. Anyway, well, I'm just gonna keep going. If you have any questions, then just ask me. So we have this texture 2D variable, we have this texture 1 variable, and it's of type texture 2D. So we've just created this our own type called texture 2D. Inside of there we have this width variable, height variable, and pixels pointer. So we have a pointer to an int. Okay. And basically we can use int pointers as arrays in C++. It's really cool. So let's create an array. I'm going to create an int array, and I'm going to say, hey, I want this array to be... Actually, here we go. Let's do this. Texture1 dot width equals 512. Okay, and we want to set the height the same thing. We want a square texture. Okay, and then we say we want an array of pixels. Okay, so we want an array of RGB pixels. So I'm going to do this. Okay, we're going to create a structure called RGBA. Let's create another structure. This is a really good example. Struct RGBA, and in here we have this float that's R, float B, float G, float A. So these represent the colors. I don't know. So pointers are useful for dealing with data. They allow you to move data around in a different way than you would be able to with normal variables. And it basically allows you to move data around through functions really easily. So basically, let's create an example here real quick. Let me just call this main1 here real quick. 1, and I'm going to create a new file. So you can have multiple files called .cpp files in your project, by the way. It doesn't have to be anything in particular. It does have to be either .cpp, .h, .hpp. There's a bunch of extensions you can look at, but just stick with .h and .cpp if you ever need to use those. Use cpp for the minute. So I'm just going to call this pointers test. Alright, so I'm going to include IOStream so I can use cout. That's what IOStream has in it. It has cout and a bunch of other functions inside of it. And we need... No, that's probably all we need for the minute. Namespace std, because remember, we don't want to be having to type std : all the freaking time. I'm going to type void main. So we don't have to return anything, so save up some time. Okay, so now I'm going to create a variable in... Actually, let's talk about arrays, because arrays and pointers are almost kind of together. They're linked in a little way. So let's create an array right now. I'm going to create this. I'm going to call it integer array. You're getting a bit of a preview of what Ram's going to go through with you guys next week. I'm going to create an int array, and the way you do arrays in C++ is you use these little square brackets like that. And inside of these square brackets, you need to type how many elements are going to be in your array. So let's create an array that has 3 elements in it. Okay, cool. So we can set this equal to this, like this, with a few brackets like that. Okay. So if you want to do it like this, if you want to space it out like that, you can do it like that. We can space it out like this. For the minute, I'm just going to do it like this. So I'm going to say our first element in our array is 1, second element is going to be 4, third element is going to be 5, and our fourth element is going to be 6. Now you're probably saying, well, why is there 6 elements when I said, why is there 4 elements when I said 3 here? Because in C++, for array indexes, this is called an array subscript, by the way, or an array index. Subscripts are denoted with 0 base notation, so I don't know if you're familiar with that idea, but it basically goes 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and that's 10 numbers, because 0 counts as its own number. So this is opposed to 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so that's what that means. So 0 corresponds to 1, 1 corresponds to 2, 2 corresponds to 3, etc. Okay, yeah, that's right. So it's called zero-based notation. And that's why when we say 3 here, it actually means... oh crap, have I just made a big error? 1. I think I did. Well, let's put 4 here, because... so, why is that? What? I think I've just confused myself. Integer array 0 equals 10. System... Pause. How have I just confused myself? I'm very silly. Hold on a sec. So integer array is 0, 1, 2, 3, right? Maybe you have to put a 4. Okay, sorry. So when you create arrays in C++, you have to create the actual number, so the real number of elements in your array as its initial subscript, and then later on when you're referring to it, you have to refer it to with zero-based notation. So for example, right now this array has 4 elements in it, so 1, 2, 3, 4, but the 0th element is 1, first element is 4. You get the idea. So it's zero-based notation when you're referring to it after you've declared it. Okay, so that was really bad on my part. I wasn't aware of that. I assumed I don't use arrays very often because I'm dealing with them implicitly, but yeah. So arrays are like this. So they're basically just like structures. Basically, it's just a structure of elements in memory. It's basically just a bunch of ints stacked up together. Okay, so think of it like this. Delete. It's basically just like a bunch of ints stacked up like this. Okay, so this would be what we call an array. It's an array of elements. Array of elements. Yes, you actually have to define its length right then and there because it needs to allocate that memory. And it's very annoying when dealing with arrays having to deal with that setting in stone because you can't actually change it. If you wanted to create an array from this array that had the same number of elements but an extra one, yeah, if we want to add an extra element to it, then we have to create an array with 5 elements, copy all the other ones over into our new one, and add our new element in it. So there's this huge rigmarole, and that goes into this idea of having these things called linked lists, and you'll come across these probably in Math for Games. We can use linked lists to represent arrays in a much more effective way because we can use them in a bit more of a dynamic way, and that comes to how C++ can be dynamic. Yeah. Sorry, what do you mean by this is so different? Right. Yeah, in C++ you've got to be a lot more careful. Yeah, that's the thing. It's yeah, exactly. It's so much easier in things like Lua because you can just do it. It's not as low level. Lua is what I would refer to as a scripting language, not necessarily a programming language. Not to offend you or anything. It's not like that. I don't mean it like that. C++ is a programming language at a low level. It's really like you're dealing with memory and dealing with stuff like that, whereas in Lua you're dealing with hypothetical objects which the Lua interpreter deals with on a memory level. Okay, so we created these arrays right now. Okay, so we have 4 elements in our array, 1, 2, 3, 4, and if we want to get the first element, we type integer array square brackets and our subscript, which is 0 to get the first element. Say I wanted to set this to 11 or something, I don't know, and we ran this, we'd find that integer array 0 is now equal to 11. So you can see it was equal to 1, 4, 5, 6. Now it's equal to 11, 4, 5, 6. So that doesn't matter. If you try and go and access number 4, you'll probably run into some issues. It'll probably just do nothing, because it's just not doing anything, basically. Let's try 5. Let's have a look at 5. Nope, doesn't matter. But you're actually accessing memory that's not there. So it's probably changing something that's adjacent to it in memory. So you've got to be really careful when you're dealing with arrays, because there isn't much error handling around that. Okay, so you need to make sure that you're only ever dealing with the size. And a handy little trick that I really suggest you write down, if you ever need to get the size of an array as an int or something, like you go, okay, so I have an int, I want to get the size of this array. I can't just go integer, say int array size equals, I can't just go integer array dot size or anything like that. I have to use a little handy trick. So I'm going to use the size of function. It's not a function, it's like a special type of function that comes with C++. And size of function returns the size of function returns the number of bytes that an object takes up. So anything you put in these brackets right now, it'll tell you how many bytes it takes up. So integer array, we want to find out how many bytes in memory that integer array takes up, and we're going to divide it by the number or the size of bytes of an integer, a regular integer. So what this is essentially saying is it's saying, okay, so we're taking the entire size of this object, which will be 4 times, so we know that an int represents 4 bytes. Okay, so just say int means 4 bytes. So that means that our total thing right now means that it's 4 times 4. So that's 16 bytes divided by 4, and we're going to get 4. 16 divided by 4 is 4, right? So our array size right now will equal 4. Okay? So this little bit of arithmetic right here is really, really handy. I'd suggest you remember it, because it basically tells you how many elements are in your array. It doesn't tell you how many elements are not equal to 0. Okay? Like for example, I can say +1 right here, and it doesn't matter because it's going to be 5 now, right? So you got to be really careful that you get this right, because if you're getting a size of an array, there's a couple of other ways of doing it which are quite complicated. But for simple arithmetic like this, and you ever need an array size, maybe if you wanted to, let's say I wanted to clone this integer array, array 2. Exactly, it's so much easier in Lua. So I'm going to create another array, and I want to give it 5 elements this time. Okay, and I'm just going to do that, and that means empty, so that sets everything to 0. Basically, what that does, everything is equal to 0. So that's the same as going 0, 0, 0, 0, 0, like that. Okay. So like that. That sets equal to 0, or everything to empty. Okay. And that's a big thing about initializing. Okay, so initializing variables in C++ is really important. You can do this, but it'll probably tell you, hey, you haven't initialized this variable. See, it says in that console window just there, if I go back to my build log, it says, hey, integer is an unreferenced local variable. Well, that means 2 things. It means it hasn't been used once, and also means it probably hasn't been set. Okay, so we need to set this to equal to nothing, like that. Cool. And then now to clone everything over from here, we have to go use our for loop. We have to go for int I equals 0, I is less than our array size. Okay, I plus I. Again, doesn't matter what order you do this in, just I typically go with plus I, because that's the industry people that I speak to all do that. And it's probably just good practice anyway, because it doesn't mean much the other way around. So now I want to clone, so we'd probably go by saying integer array 0, or excuse me, we need to do a few things here. We need to check if our, no, actually that's fine, it doesn't matter. So we got to say integer array I, so we're using a for loop right now. This is really cool. So we're using a for loop. We're saying our ith element in our array, we're going to set that, we're going to set a new array of I. So we're going to create new array I is equal to old array I. So since we're dealing with this array size variable, which is currently equal to 4. Okay, so it's just going to go through this loop 4 times, and then you'll see if I just run this program right now, you'll see what happens is our new integer array has now got 1, 4, 5, 6, 0, because we initialized everything to 0, so it's just cloned all these variables over, okay? All these, sorry, not variables, all these integer variables over, not variables, but you know what I'm saying. And now, say for example, we wanted to make our 5th element, we'd go integer array 2, 4 for our zero-based notation, so it's technically 4 plus 1 is what we're using, equals, I don't know, 10. So now if we ran this function, or ran this program, you'd see that integer array 2 now is 1, 4, 5, 6, 10. Okay? So does that make sense? Do arrays make sense? What kind of question is that? Awesome. So now we understand how arrays work. Let's understand how pointers work. So say, okay, I want to create a function that adds arrays together. Okay, so we've got these two arrays. Let's create a function called, we'll call it sum arrays. So we'll create an int sum array. Okay, so it takes, so you might immediately, there's a few ways of doing this. So we can say array1, like that, int array2, like that, and we also need an int array size. So this is one way of giving a function arrays, but this is really bad because this array1 variable right here is interesting. So you really need to not be using it like that. You should be using it like this. You should be going int pointer array2. We also need this array size variable regardless, and these arrays need to be the same size because it won't work otherwise. So I'm going to create two variables here. I'm going to create this one 4 again. I'm going to get rid of that. So essentially we've just cloned these two arrays right here. So array 4 we've set integer array to this, basically, in a really long haul way. So now say I wanted to call sum array, and I'm going to give it one array. I'm going to give it integer array 1 and integer array 2, and our size, which is array size. But in this case you'd probably just put 4 here, because, or 4 because we know it's 4. Well, put 3 because it's 0 based. Okay. So then we're saying, hey, execute sum array, here's our variables, we want the sum of these arrays. So we're going to say, hey, for int I equals 0, I is less than less than or equal to array size. Actually, that's probably not a good idea. Let's go array size like that, and we'll set this equal to 4. Because basically what's going to happen now is, because this is 0, we're going to go through here and we're going to execute it 3 times. Sorry, it's going to go, because this is equal to 0, it's going to go, hey, 0, plus plus 1, 2 plus plus 1, 3 plus plus 1, 4 plus plus 1. Sorry, it's going to go 3, because we're saying as long as it's less than. So if we say less than or equal to, it'll say, hey, go up to and including 4. If we say just less than, then it's just going to go up to 3, which is 0, 1, 2, 3, 4. Sorry, 0, 1, 2, 3, which is 4. Whereas it would go 0, 1, 2, 3, 4, which is 5. So you got to be really thinking about this logic here, because it can be quite downfall. That can be your downfall. So now we want to say, hey, I'm going to create a variable called summation equals 0. I'm going to say, hey, summation plus equals and array 1 I plus array 2 I. So what that's saying is it's saying, hey, the ith element of both of these arrays plus together plus our summation will, and then we're just going to return summation, and that's going to sum our arrays together. So let's say we probably expect our results to be 2, 8, oh, 8, 10, and 12, because we have these duplicate arrays right now. So it's basically integer array is equal to integer array 2, or the other way around. So if I ran this program right now, and I make sure I get to the result, so int sum equals that, ran this program, we would see that 12 plus 8, which is 10, plus 10 is 20, plus 12 is 32. So sum should equal 32. Oh, there we go. Look, it does. So we've just summed these arrays together really quickly, and we've given it these two array pointers. Okay, this is a much more effective way of doing it, and you can see how pointers are useful for passing around information. Another way we can use pointers. So that's how arrays work. So mark ending array talk. Okay. So now let's get back to some basic pointer arithmetic. So I'm going to create an int. I'm going to call it number of employees. So go to 10. And then I'm going to say, hey, I'm going to get employee count. I'm going to say number of employees. So here's a problem. How, in our scope right here, can we create a variable that easily represents this number of employees counts? Yeah, we could probably come in here and we could say, okay, well, get employee count returns. So basically what get employee count is going to do is it's going to say, hey, query the database for how many employees we currently have, and it might be different to 10, and that's just going to say, hey, just return the new number. Maybe instead of having this function that returns something, we can create a function that doesn't return anything, that changes a variable that we already have. So here's where pointers come in, and this is a really good example for pointers. So and it's going to take an int reference, number of current variable. Okay, so here's where pointers come in. So references and pointers are essentially the same thing, but don't think of them like that. Think of them like two separate things, but they're also kind of connected. Okay, so get employee count, we're just going to say, hey, pretend this queries a database, database of employees. Let's say, hey, it came out as returns 10. So we'll say employee number equals 10. So we want this variable right here that we've already created to be equal to, oh, so let's make that 20, just because we don't want it to be the same as this. So now our database returned 20. How can we make this variable that we've already created out here, that's already linked up to our program and everything, really easily equal to our new value? Well, that's where pointers come in, and references as well. So we make this an int reference, and we say variable equals employee numbers, like that. And this function doesn't return a thing, it doesn't do anything, but when we run our program right now, you can see that number of employees is currently equal to 10. If we ran our program right now, we execute this function, see number of employees is actually now equal to 20. Huh. That's where pointers come in. Okay, so this, we're passing right now into our program here a reference to an integer. Okay, so and what a reference to an integer is, it's like saying, hey, use this variable that I've already created as this. So if I change this from an int reference to a normal int, and I ran this program, you'll see that literally nothing changes, because this variable that we've created here goes out of scope, which means that it's immediately deleted as soon as this function ends. So any variables you create in here are immediately deleted when it hits this bracket. Okay, so basically when we pass in an int reference, it says, hey, this isn't a variable that needs to be deleted, it's already created, and here's the memory location of it. So change this variable, not create a new one and doing that. Okay, so does that make sense? I hope that makes sense. I know that's super duper weird, but I hope that makes a bit more sense of how pointers can be useful in passing around lots of data. They're not temp variables, they're variables that we've already created. So basically, if I just snipping tool this guy right quick, go hey, right there, I'm basically saying, hey, give me this variable already created here and just set it equal to 20. Okay, so we're just giving it this variable that we've already created, as opposed to getting rid of that reference ampersand there, and we run this program. You can see it doesn't change anything. See, employee numbers is still equal to 10, whereas if we're giving it a reference to a variable that's already created, it's actually changing that variable right out here already. So it's the same as going and saying, hey, returning that number. So maybe returning employee numbers, return employee numbers, and then saying number of employees equals that, and you can see that that's going to return the same result. But you can see that's actually that makes more sense, but you can see that this way can sometimes be more effective when you're dealing with a data structure that's already been established. So say maybe a game engine or something, you've made this game engine, it's got these variables in it that you can't just deal with it like that. Okay, so that's referencing, and that's how they can be used, and they're very much the same thing. So let's go back to data structures. Okay, so say now we've got, you understand how RGB works, right? You've heard of, your red, green, blue colors and how they make up every color of the rainbow pretty much. Well, all 16 million or whatever there is something like that. Of a computer monitor. Most computer monitors these days use RGBA, which, well, they use a standard called Adobe sRGB, which is a standard that they've created that does that. So RGBA just stands for red, green, blue, alpha, which stands for its opacity. So now we want to create an array of RGBA objects. So think of it like an object. So this is an RGBA object. So this is a pixel. Actually, this should probably be called pixel. Okay, so pixels. So we're going to create an array of pixels with each an RGBA. So essentially, this is the same as creating an array, basically, but without the brackets or anything. If you put brackets here, it's actually a different thing, and it's not correct. So we want to create an array of pixels. Pixel. This will be our pixels. And we're going to create an array of pixels that is. We're going to create a multi-dimensional array right now. So we want this to be texture width, which isn't a constant. That's not going to work. So let's get some constant variables here. Well, since we're setting it here, so basically, if you want to create a variable like out here, int size equals 10. If you want to create this as a variable, it has to be a const. Okay, it has to be a constant variable for it to work inside of here. So, so I'm just going to put 512 here for the minute, so I don't have to create a new variable. 512. So think of this like we're creating so we're saying 512 times 512 is how many pixels we want. See, this is what we're doing right now. 512 elements on the width by 512 on the length. Okay, so it's like a list of lists. So we're creating a list of 512 elements 512 times. So we're creating a picture, basically, if you think of it like that. Okay, and I'm just going to set that equal to nothing. And I'm going to say, hey, interpret. Let's see if we can come up with a function that goes through and randomly generates all of these elements. I'm trying to think of the quickest way of doing that. Anyway, so we've got this pixels array right now. I do want to do that because I want to show you what it looks like in a file. So, and then we'll wrap up because it's almost 11 o'clock where I am right now. So get pixel. Yeah, it's exactly like a grid. Colors. Let's just say get pixel colors, and we'll give it a pixels array and random pixel colors. So I'm going to create a function up here. It's called void random pixel colors. and then we're going to take a pixel pointer, because we want to take an array of pixels, and we probably also need an array size. So multi-dimensional arrays are different. Also, you should be using the size underscore t variable to deal with arrays and stuff like that, because they're unsigned integers, which means you can't have negative numbers. So I'm sure you understand the difference between an unsigned and a signed variable. So a signed integer means there can be negatives and positives, and an unsigned variable means an unsigned integer is a number that's only positives, and it nets you. So basically, we talked about how integers represent 4 bytes. There basically means that in those 4 bytes, we can either choose to represent negatives and positives, or only positives, and there's no only negatives because that's pointless, no one needs those, right? So, yeah, so you understand how that happens. So we're going to create a function that goes for int I equals 0, I is less than array size array I plus plus. Now here's an interesting thing. Right now, if we wanted to address, so we have an array of pixels right now, right? So let me type it out for you. It's signed and unsigned. That. So unsigned equals positives, numbers, and negative numbers. That's assigned. Unsigned is only positives. Okay, so we want to address these. There's going to be 2 variables in here. We're going to have a nested for loops right now. This is cool. I is less than array size. Size I plus plus. And so we have 2. Since we have this variable that has a list of 512 elements 512 times, okay, you can see how we have to actually have 2 for loops to address that. So we have an I and a j variable. So to address this, we're going to say pixels I j, like that, is equal to this. Is equal to new, or is equal to pixel. Dale, come on, there we go. So we have some issues here. What's the issue? Oh, actually, we need to have a pointer because we have a 2-dimensional array. So since we have this 2-dimensional array right now, that's interesting. Let me do a quick Google here, real quick. Man, it's a common search term. Okay. So, if we want to create, if we want to pass a variable or a list of lists, or an array of arrays, we need to actually give it the subscript range in here. So that's going to be, that's tough. We do it like that? No, we have to specify the number of columns. Okay. We say const int size. Can we say size in here? No, we can't. That's annoying. Okay, so how do we deal with that? Interesting problem. Well, what I would probably do say here. So I'd probably create some kind of let's just say hypothetically we always knew that this was going to be 512 by 512. Okay, right, that makes sense. So let's pretend like we always knew, hey, this is always going to be 512 by 512, always. So our array size is always going to be 512. So this is a hard-coded function, which is never a good idea, but let's just hypothetically think that this is that's going to happen. So basically now I have to create a pixel variable right here. Pixel p. I'm going to say, hey, p equals rand, or p dot r equals rand, p dot g equals rand, p dot b equals rand. So I'm just getting a bunch of random numbers right now. A equals 1. And we'll make sure the alpha is always 1, just because that means it's always going to be set to something. Then we're going to say that's equal to p. Cool, so now this random colors function executes a bunch of stuff. Okay? If we run this program, this probably might take a little while actually. I didn't even anticipate that. Oh, we got an error. Oh no. Oh, I see what's happening. Right. Well, firstly, this is main 1. No wonder it's not executing. Let's do main 1. And this runs. Run. And let's have a look. Oh, here we go. Look at this. Oh, Stack Overflow. Oh, crazy. So we got Stack Overflow. Now, what that means is it means we can't actually do that much, which is really interesting. And that's all that's going to happen if you ever go over or something. It's just going to do that, right? So let's have a little look and just see where our Stack Overflow is happening. Okay, so it's happening even before our for loop right now. So set a breakpoint right there. Hey, run. Oh, look at that. Stack Overflow immediately. So let's break there. Stack Overflow again. Huh. That's really interesting. We just keep getting them, huh? Wow. We just keep getting them. That's really cool. Okay, so this is called debugging exercise. So why do we get this crazy Stack Overflow? Let's consult the Stack Overflow. Yes, it is. It is indeed because of memory. So here's probably the problem. Let's just go ahead and Control K, Control C that, and again here, oh. Control K, highlighting a line, pressing Control K, and then Control C comments the entire line out. Run this right now. We should not get a Stack Overflow again. Yes. Okay. So the thing with Stack Overflows is that. No, you're correct, it was memory. Stack Overflows occur because of memory. And this function that we declared up here, it can't be stored in memory because it's recursive. It can't be compiled because there's no exit path. Or it overflows, basically. And that's probably something to do with our columns like that. So, okay, so we... So sorry, I'm just doing a bit of research. Yeah, that's correct. first I'm going to go plus plus I for continuity. Oh, I think I see what I did wrong. Well, first of all, I didn't put a J there. And then make that I. Okay. So now let's run this guy and see if we get a Stack Overflow again. Oh, we did. Okay. So, hey, thanks, Cortana. Help a pointer to array, or simply pass an array through a single pointer. Okay. Right, int p. So we can just do int pointer or pixel pointer array. You can do that, but that doesn't match. See, this is great debugging. Pile time. So we do have to specify rows and columns. So int rows, int columns. Did I spell columns right? I think I did. Doesn't matter. Int pixel. I keep saying int out of habit. I thought you could do that. I swear to God, you could do a pointer, and then you could just give it, yeah, but it doesn't like that, does it? That's really weird. Huh. This is cool. See, I like these sort of issues that I get, because then it's like, whoa, how do I solve this? It's like almost, it seems impossible. Oh, you know, there's definitely going to be 512 rows of 512 pixels. That's a big array. Okay, so let's make that an int just because, just for testing. See, I'm always wrong. Things like this. I bet you Noman would have had this issue as well, but just problems like this that come up are really fun to solve because, and I think that's what the essence of C is. It's like solving issues like this. Multi-dimensional. So basically, if you ever have an issue, just literally spit it into Google and then just like put C++ after it, and then you'll get a bloody thing. You'll get a Stack Overflow article. With lots of issues. Yeah, it's a bit of a weirdie because I've never dealt with this before, so that's really cool. It's very rare that I see problems like this that I haven't dealt with before, which is really good. Okay, so I got Stack Overflow, multi-dimensional with, let's say, 2D arrays, C++. Let's like that. Three ways to pass a 2D array to a function. Okay, so parameter is a 2D array. Create an array, pass func array. Parameter. Oh, you know what it might be? Let's try something. Let's try moving this function definition down here and having, well, first of all, let's clean this up a little bit, and having this, grab that. This might be a little C++ quirk right here where it gets Stack Overflows before things even happen. Because it maybe might need one of these defined before it can like do it or something. I don't know. I'm just like thinking out loud right now. So let's run this guy and theoretically. Okay, cool. We still get one. Let's say just no row subscript. You know, there's probably some super simple answer to this, and I've just totally forgotten how to do it. That's usually what the thing is. Okay, there we go. So much for wrapping up by 11 o'clock. That's okay. I want to solve this problem. Pointer. Yeah, I think we have to do that. Pointer. How does it say to do it? It's pointer to pixels to 512. That should work. Let's see. Stack Overflow, betcha. There we go. Stack Overflow. Okay. Right. So our stack frames. It works main. It does that. See, that's why they have all these little tests, so you can't actually hurt anything, because that's what this is for. That's why it's spitting this error at me, because it knows I've done something wrong, or I've assigned memory incorrectly. So, let's get rid of that. Let's close that guy. The worst thing about these is it's really hard to debug them, because they're mostly broken all the time. Hey, did we get another Stack Overflow, or did I crash Visual Studio? No, I got another one. There we go, so... check... Let's have a look. Okay. Problem solved. Thanks to code for code, I actually got a problem while comparing with code. Here we go. What's the issue? So I'm not exactly sure, but this particular problem with your implementation, your merge sort, it's implementations following. So it's 20,000. Actually working with a normal C++ array which will be stored in the stack, thus the problem. Oh, I think I see what my issue is. Okay, so the reason why I think this is happening is because we might even be getting a Stack Overflow because of that. Yeah, look, it's because of that that we're getting this issue. And what's happening is that we're defining this variable, and this is a good example of how C++ actually works, or how the compiler compiles code. So when you compile a file, what happens is compilation unit, which is what CPPs are. So what happens is it will go through and it will run checks on everything. And what's actually happened right here is we've allocated this variable that's on a regular C++ array, but on the stack. So there's actually two types of memory. There's stack and then there's heap. So stack memory is memory that is defined. Let me give you a little diagram here real quick. Okay, here. So stack memory is used to define static. I think it's static memory allocation, and heap is for dynamic stuff. So what happens is when you compile your code right here, it's defining all this stuff on the stack, and it is absolutely huge, and it's running out of space. We need to put it on the dynamic memory in order for it to be able to use it. So we actually need to create a new pixel array of arrays that is 512 by 512, and we should, what's the issue? I think we just need to do that. New pointer. Oh boy, hold on, let me look at this. So how to create new brackets multi So it's overflowing because it's assigning too much memory in big places, basically. It's a really interesting problem. So we need to create a pointer. That's what I want. Pixel pointer array, like that. And I think then we gotta go pixels pointer pixels. Initialization with expected aggregate object. Oh, I see. What am I doing? It's sort of an automatic one. Like it's like, hey, your program needs this much memory on the stack, and then on the heap is like, hey, this is the memory that this is your computer's memory that you can access. It does like this extra stuff, but the stack is like, this is the set amount your program has that includes like the code and any other stuff. So we've created this variable that's like way too big to handle. Although it's not really that big. Well, it's actually pretty big, really, when you think about it. It's quite a large variable. Multi-dimensional. See, these are issues that people encounter all the time. Or, well, I don't encounter them all the time, but this is something that I think they really should go through with you guys, because this is an interesting error that I've come up with right now. And if you know, I've never experienced it before. I've been using C++ for a really long time. So, yeah, really interesting problem. So I think what's happened is like, how do we do that? There we go. That's probably how we do it. All right, let's just give this a go. Let's give this a go. Pixels 512. There we go. And we're just gonna copy this definition down to here. And with that, let's hope for the best. Please tell me we didn't get stuck overflow. I think we did. Yeah, we did. Looks like I had a different memory address there. So we're still having trouble how to Dave. Why am I Dave all of a sudden? Ugh. How to create multi-dimensional arrays of structs. Haha. Here we go. So, we need to create, well, first of all, I probably should have done my struct a little bit better here. Type def struct these are called opaque structs, and the reason why they're called opaque structs is because they're actual types rather than defining it the way it was before. And now this type that we've just created is different. It's actually like physically different. Likewise with this one, we should do the same thing. Type def. Type def allows you to define your own types. It allows you to rename types as well. Like for example, I could create my own type, like type def int, and I'm gonna call it maybe int4 or something like that. Excuse me. Yeah, that's right. So int4 now is essentially an int, but we've called it int4. So if we went down here and we used it like a regular int, we just call it int4. Hey, x equals 10, and it would do the same thing, except we've just called it int4, and we've created our own separate type. So this is useful when you're dealing with engines and big software projects that require big, long things like that you want to keep continuity and make it easier to read. That's why type defs are really cool. And I won't call it capital texture 2D, I'll call it texture 2D like that. Alright, so the problem that we're encountering right now is that we can't actually allocate this much memory on the stack, so we actually have to create a dynamic pointer right now. So that's how we do that. It's the other way. Whoop. Pointer, like that. And it's like that. And this is going to equal to pixel pointer. We're just casting it. We're just going to call it malloc. So right now we're creating a dynamically allocated memory. Dynamically allocated memory requires this malloc function right here. And we're going to take, we want 512 times the size of pixel pointer. And, oh, we don't need a brackets or anything there. What am I doing? Okay, so now pixels won't work. We need to take pointer. Okay, we're getting there, almost there. We also need to actually create a quick little for loop here. I is less than 512 possible I. We don't need brackets. You can do shorthand stuff in C++. This is a really cool thing. Shorthand is really handy. Here we go, almost there. I think we've almost solved the problem. Cars to pixel. Malloc. 512 times. Wait. So, for every element in our list, we want, yes, that's correct, we do actually physically want 512 times the size of pixel. So, like, you can see that how large these things are going. I know this totally doesn't make any sense at all, but just like that problem solving process that I'm going through, pay attention to how that works. How I'm going and I'm looking online and I'm, taking some time to really focus and look online and what's happening, stuff like that. Okay, so now when we run this, we shouldn't run into any issues. I say that with great doubt. Yes, there we go. Cool. So we got no issues now. Holy shit. That was a fucking crazy ass thing to do that. So now let me put a breakpoint right here. And, yeah, you don't understand what I'm doing. I'm doing some pretty advanced shit right now. So don't get confused. Don't try to look at this too much. But now you can see we've generated a bunch of random data right here. Like crazy stuff. Actually, you know what? I probably want to change that rand from rand, no, normal rand. I want to change it from 0.0 to 1.0. So the way we do that is we go modulus. We were doing this in class today. We give it a number. So we want it to generate from 1.0 f plus 1.0 f minus 1.0 f. You don't need those. 1.0 f 0 f. Actually, I think I don't even remember what I said. Holy shit! I am really losing it tonight, huh? Man, what did I say in class? It was largest number, and then I think it was like smallest number. Rand. Numbers in a range is I thought it was minus the smallest number, so 0.0 f plus 0.0 f. Now that makes sense. Here's a good thing. Must be integral scope. It must be integral scope. This is really cool. So what's happening here is it actually can't like do this because it's not in a correct scope. So we actually need to create like float f equals rand. I'm pretty sure this won't work. It's the same problem. Yeah, we're not in integral scope. Oh, well, how did I... Is it because of the zeros and ones? Okay. Okay, that's okay. You know, that's fine. Get... let's just get a float... get random pixel value. Cool. Return that. Is that still not in integral scope? Okay, that's really interesting. One 0 plus 0. That's what we want. Okay. Cool. So can we do random rand with float? I know there is a way to do it. It's... I thought it was rand, but then... right. All sorts of stuff I'm learning tonight. Yeah, I could use random ints, but I want to use it as a float. I'm trying to generate a random float. That's what I want right there. That. Okay, so basically, let me explain what this is doing. So this get random pixel value right here is going to generate a number between it's going to generate a number between 0 and 1. Okay. Right here. So rand max is just basically then the biggest number you can have that random can generate. It's a macro. I know that totally doesn't make any sense. Like random. This should generate a random float, because this static cast turns that like into a. It doesn't really make much sense, I know, but here I'll show you what static cast does. Okay, let's bring up. And if you type in anything in Google, it usually brings you to a CPP reference page, and this will tell you like a bit more information about a function or a piece of code. So static cast says, hey, only the following conversion someone's conversion to if there is implicit conversion sequence from expression to new type, or if overload resolution from direct initialization of an object, the reference type is new. Okay, so it's basically just like cutting out that data loss that happens. If that makes sense. Not really, but it basically just cuts out a bit of data loss, and you don't need to use static cast ever. It's like one of those things that no one ever uses, but just bear it in mind, it exists. It's just like what's something that you know exists but you don't care about. That's what it's like. It's just like, great, it's there, cool, thanks for letting me know. Alright, so now we've got these random pixels, right? Got these random pixels. We've got this crazy array of pixels. Look at that. Look at that, man. That's exactly what we want. That kind of number. Perfect. Yeah, static cast exists. Free static cast. Hashtag free static cast. Okay, so now we're going to write it to a file. Whew, this is going to be fun. Alright, so to write things to files in C++, you have to include a few things. You need to include the fstream header. Fstream, another C++ only thing. There's also files, but we'll get to that later. So we want to write this to, so comment as we go, write to file. So we're going to create an fstream object. Actually, we only need an ofstream object right now. We'll call this file stream, and we'll say equals of stream brackets, and we're going to give it a file name, and I'm just going to put this as bin / it should take a string. Yeah, it does. Bin / texture1 dot. I don't know, let's create up some crazy texture. We'll call it txt2d or something like that. So this is our imaginary texture file. We need to open it up with iOS binary and iOS in. I think that's what we need to do. I think it needs to be the other way around as well. But we should just be able to stream. I don't use this very much. I barely ever write to files, and it's one of those things I really need to get better at, but I just haven't really done it much. But in the meantime, we'll just, while that page is loading, if file stream dot open is open, sorry. So this is saying this function right here returns if this successfully found that file and opened it. Okay. And what that basically means is it just says, hey, if it successfully found the file and successfully opened it, then good. Okay. then we want to do this code in here. This is a way for us to negate the need to worry about I/O exception errors that come up. Yeah. Okay, so here's what we need to do. We need iOS out. iOS app, what does that do? That's all performed at the end of the file appending. Oh, we don't need that. We also need binary. There we go. There we go, baby. We got it. We got it. Okay, filestream.write. And here's where it gets really cool, because this is like the cool shit right now. So, we now need to take our texture1 object. Well, actually, first of all, need to say, hey, texture1 dot pixels equals pixels, and that's not going to work, so we need to make this a pointer. Cool, that works now. So now we need to take hey pixels, or hey texture1, we're going to cast this to a const char star, I'm just going to call it texture1, we're going to go to reference, that's pretty necessary, and our stream counter, oh, good question. Stream.write. We just see what that number needs to be. See, I'm just typing it into Google and it's going to bring me to the page where I need it. Come on. This is a notoriously slow website. You can see just by looking at it that it's old. Okay, so number of characters to insert. Oh, right. So that's just going to be the strlen of that. I think. Well, we'll see how we go. So now basically what this is going to do, if we run this, hopefully we'll see file stream. Ooh, I don't think it worked. Let's go into my, where this program, what am I saying, program is. Debug, and then in here it should have created a folder called bin. Let's go back. Example. Here we go. We should probably do that. Let's just do the normal way, so I'm not going to be weird. Okay, right. So file stream, and then file stream.open, like that, and there we go. Right. So now when we run this, so file stream's still equal to nothing. That's really weird. So basically what's happening is this isn't even writing. If we set breakpoint here, yeah, it's not even like writing to that. It like just can't find it. I think it's because of the directory. Let me create a directory in here called bin. If I run, wait, where is it? It's out here? What's it doing out here? Let me fix that up. That's wrong. I don't want it to be outputting out there. Oh, they still haven't fixed that, have they? Of course not. Alright. Almost done. Literally almost done. I'm very ready to go to bed. Okay, so yep, that's what we want to be building. Cool. Right, so let me just make sure that this is not building here for some reason. It is building there for some reason. I guess that's because that's where our solution directory is. Yeah. That's kind of a bit annoying. So need a folder in there called bin. And, oh shit. So it's like not opening. Okay, that's really interesting. So how about we say, hey, that's pretty good. We could do that, but that's lazy. Binary, let's... Oh man, my mouse, I need a mouse pad real bad. Plus plus, binary files, right. Okay, that's a good question. So with an endless side scroller, how could we create more world if we can't extend an array? Would it be to copy the world but defined with more space? See, in the way that I would write that is I wouldn't actually necessarily think of it like an array, because if you're dealing with a world, your world in the wider sense is actually just zeros and ones. So in a file, it'll be like a scene file. Like, for example, in Unity, when you open up Unity, you open up this .unity file, and it's binary and it represents your entire world, game objects, and everything. So if you're creating an endless side scroller, you would basically just not represent it with an array, because you just like clone the objects, like you just clone the floor and just keep cloning it until you need it to stop, and you delete the ones behind you so you wouldn't run out of memory. So yeah. Right, so alright, so okay, so let's just get rid of that. Let's go texture 2d.bin. And how about we just not check? I thought it was like that. That's what I thought. Right, there we go. Okay, so now let's have a look if there's a bin file somewhere in here. In here, isn't it? So anywhere at all. File called texture2d.bin. Let's have a look here at any .bins. Nothing. Oh, that's interesting. Again, another thing I really need to get better at. Well, see, you wouldn't need to order them because it would be defined based on the coordinates in the world. Like, you represent it with a button. And when you get to math for games, you'll understand this a little more. I won't be able to explain it as good as one of those guys might be able to. But yeah, it really is a bit more objective than having to represent it in an array. Yeah. But you guys will get to that. I don't want to sit here and explain that because that's boring. Oh, well, that's probably a problem then. We can't use the one. What am I saying? Oh, that's where my issue has been the whole time, hasn't it? Okay. There we go. Texture 2D. TXT2D. Right, and then we're going to say, hey, if file stream dot is open. Right. F5. There we go. File stream is not. Oh, it is equal to null still. How? Let's just have a quick check and see if there is anything. Ah, look, there it is. Right there. But it didn't write anything. That's interesting. So there's our file, but it didn't actually write anything to the file. That's okay, I know why. So let's just get rid of that whole crap there. Alright. Let me clean up my project directories a little bit here. Just clear this out a little bit. Let's run this again. Right. So God, I can't wait to like fucking take math for games and really get better at this. Oh man. Okay. Oh, I think yeah. Well, that's a problem anyway. The size of. Do 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 do. Alright, so let's run that. Continue. Let's see. We got some kind of result. Please. Nothing. Oh. Let's just write it to a file like this then. File. There we go. It's still writing nothing though. So that's really interesting. Huh. Const just equals const just texture 2D. Right here. This will probably give me a Stack Overflow. This might, no. Ah, well, see, that's probably why. Is it because it's not casting to a chart or something, maybe? No, it's just nothing. Yeah, I might try doing that. Let's try just quickly, just y equals this. There we go, that'll work. And we want to do that. This is y. Okay, let's have a look. Cool, so now if we go ahead and we have a look. Yeah. Oh, there's something. Don't know if that's what we want though. That's all. Whoops. Oh my gosh, my mouse is killing me right now. It's like all of a sudden just stopped working on my desk. Like real weird. Okay, so we're writing something to it. But this texture 1 object is not representing anything. For some reason, like maybe it just like can't, because it's so big it just can't handle it. But I don't know if that's how it works. It doesn't do that. I've dealt with larger data structures before. Let's try doing it with read and write instead of using the new shit. Let's use files. File equals f open. F open, we want a file name and we want R. Right, we want R. Right. And this will be bin / oh, we'll just do text texture 2d 1.txt 2d, and then this is something I'm much more familiar with. File. Oh, it's fwrite. fwrite, and our buffer is just going to be a pointer to texture 1, and our element size is just going to be the size of our struct, which is going to be, actually I don't know if that's accurate. It needs to be like the size of texture 1 because it's, and then 1, and our file stream is file. So let's run this and let's see what happens. Oh, that's right, that stuff sucks. Underscore s. Oh, I hate you. No, we're not doing that. I'm just gonna grab this message. Hold on. So when dealing with older stuff, it'll give you these CRT underscore no warnings messages, and basically what that means is it's just the old C++ stuff gotten rid of, and they don't want you to use it anymore. But it's like more superior than the new stuff is, so they're just being cocky. So you just gotta add that message to your preprocessor, and it works fine. So let's do it here, and still not writing anything. It's not writing anything. Oh man. Well, wonder what the size of this is. Let's stick this into size of. This might be an interesting exercise because I think I know what the answer to this problem is already. But let's have a look. Size. Let's go T. Bet you didn't expect doing this. watching me solve errors. No, this is just me being stupid. They're not complicated. I'm just not realizing what I'm doing. So x is 4. Huh. That's really interesting. The size of this is 4. Okay. Well, that's really interesting. I might leave this because I don't want to blow my own brain up, and tonight, kind of not really in the mood for it. So let's just try the size of pixels. This should be a pretty big number because it's a fair bit of RAM. Still 4. Huh. That's really weird. Because I'm literally allocating more than 4 memory right here. It says there's more than 4. Let's try a reference to pixels. Let's try that. 4. Let's just try pixel, because it should be float times 4. 16. Right, that's correct. See, that's correct. Float times 4. Yeah, we got so close. I'm almost there. Okay, so this is correct. So I think it does need to be like that. Size of... It's cold in here, so I gotta get under the blankets. It's just like not writing anything. It's really interesting to see. Like, it should be writing something. Like, it should be writing something. If anything, it should just be writing absolutely something. But it's not writing anything. So, that's really interesting. Nothing at all, huh? You don't want to write a single damn thing to the file. Huh. Darn tootin'. Let's just make this a regular struct rather than an opaque struct. That might solve some problems. Let's give that a wonder. Yeah, it should like be doing at least something, because it should be writing right, not writing anything. Above is a flush, so the file is read. I just reckon it just like can't handle like the size of this thing, and it's just like saying, nah, it's not anything. This is called integer overflow. But it should not be doing that. Pixels should be an insanely huge variable, but it's like not, because it's 512 times the size of a regular pixel pointer. which is a fair bit. So let's do another test here. Int x s equals size of pixels, pixel pointer 4. Really likes that number, huh? Yeah, that's right. Pixel pointer is not 4. Pixel pointer is definitely not 4. Well, at least it shouldn't be. Because a pixel pointer is equivalent to the same amount of memory. Or, no, I think that might be right. Okay, so that's a pixel pointer. Let's try that. This should probably not be 4. You know, I think I'm going to come back to this. I'm going to come back to this, and I'm going to record how I fixed it. I'm going to post it after this onto this channel, okay? So I'm gonna go yeah. Thanks for sticking with me for 3 hours. Holy shit. That went really, really, really slow, I'm sure, for you. Anyway, I'll let you go. I'm gonna go to bed, and I'm gonna wake up tomorrow. I'm gonna solve this problem, and we're gonna write some textures to some files. Good stream, thanks. Alright, see you later.